All right, so let's do another example of conservation of mass for finite control volume. This time it's going to be a little less convenient than the last. So just a reminder, conservation of mass for finite control volume gives us the integral form of the equation here, which looks like the rate of change, d by dt, of the mass of the system, integral of rho dv over the entire volume. That's the mass of the system, rate of change. And then that's equal to all the mass flows that are crossing it. And if you look at this, you can see rho VA hiding inside. The integral means do this over the entire area of our thing, especially all of the inlet and outlet areas. And this dot product just says that the only part that actually contributes to mass entering and leaving the system is the component of velocity that is normal to the area. So let's do something with that. Here's a problem where we've got a bend, a change in area, and so this is a little bit more of a challenge because it's not as convenient in our xy coordinate system when we define our normal vectors, which are going to go into this v dot n business, right? So a normal vector always points out, and we can see that our first one here is just going to look like n hat 1. The problem is the second vector at station 2 points at an angle, n hat 2. And so one of the things that we can do is we can make this a little more convenient for ourselves by defining a new coordinate direction that we just call E2. And E2 is just a combination of I and j. What kind of combination? Well, you know, a cosine theta I plus a sine theta j. And the beauty is, by packaging all that in here, conceptually we know that it's the sine and cosine business, but what you're going to discover is we're not actually going to have to use it. So let's start this problem where we would start any problem, which is by conserving mass. Conserve mass. And so we've got d by dt, integral over the volume of rho dv plus the integral over the area, rho v dot n dA, and all of that has to equal 0. So let's start by applying our assumptions. The first one is that it's incompressible. That says that the density remains constant. Well, shouldn't cross it out yet. Let's start with steady. Steady lets us get rid of this whole term because d by dt is 0, so steady. Now that that's been done, the incompressible lets us pull the rho out of both integrals, and since it's equal to 0 on this side, it just disappears. So incompressible lets us do those two. And so what we're left with then, we'll use the uniform assumption in a minute, is that the integral over the area of v dot n dA has to equal 0. And as you know, the integral over an area, or over the areas like this, could be written as the sum of multiple integrals. We can split sums apart. And so when we do that, technically we have 4 faces here, 1, 2, and then the top and bottom. But we already know no mass is crossing those because they're not inlets or outlets. And so we can break this integral into 2 integrals, one that looks like the integral over a1 of v1 dot n1 dA, and then the integral over a2 of v2 dot n2 dA, and that has to equal 0. Now's when we get to play the vector games. So let's write all of our things in terms of the vector notation here. Just going to scroll down a little bit to give us some room. Okay, so let's start with v1. I want you to pay attention here because I do the same process every time, and that way I never get confused. v1 is purely horizontal. We use u to represent the magnitude of an x velocity, so we'll call it u1, and it's in the direction of x, which gets a coordinate vector of I hat. n1, well, that's purely horizontal, but it's pointing in the negative direction because unit vectors always point out of our system. And so n1 is equal to a negative I hat. And that lets us say that v1 dotted with n1, which is the whole thing inside that integral, is equal to u1 I hat dotted with negative I hat I dot I is just 1, and we've got a minus sign in there, so we get minus U1. Now for the trick that I wanted to show you about station 2. We can write that V2 is equal to the magnitude of V2, which let's just call it V2, and the direction that it goes in. Well, the direction it goes in is this cosine I sine theta j business. That's inconvenient. Let's just say it's in the E2 direction, so E hat 2. The reason this is convenient is because when we look at normal vector 2, guess what direction it's in? It's also in E hat 2. And so what happens is the dot product saves us from actually having to do this trig, right? Because if we go V2 dotted with N2, scroll down so I can write here, making these substitutions, that's equal to magnitude V2 times E hat 2 dotted with E hat 2, and E hat dot E hat, that's just a 1, and so all this just becomes the magnitude V2. So now we can take what we've just discovered and sub it in here. V dot N at station 1 is just equal to minus U1, so we can write integral over A1 of minus U1 dA. V2 dot N2 is just equal to the magnitude V2, and so that's the integral of over A2 of V2 dA, and that's equal to 0. This is where the uniform comes in. The fact that these are uniform instead of some more complicated flow that varies in magnitude over the areas that it's going through is that we can move them outside the integrals because they're not functions of the area. And what that does very conveniently is just let us write that minus U1 integral over A1 dA plus V2 integral over A2 dA is equal to 0. And then, you know, we can perform this integral. The integral of dA over A is just A, so this is minus U1 A1 plus V2 A2. And that's still equal to 0. And you might have seen this coming, right? This is the old classic V1 A1 equals V2 A2 kind of thing. But we've just done it, and if this were a more complex profile, we could have subbed in dAs, which would have looked like dx by dz, by the way, and then we could have had some functionality for U1 and V2 that would have caused them to vary over this area.